Hello everyone, welcome to the course of Digital Signal Processing. Today we will start lecture number 11, chapter number 3, ZTransform. In previous lecture we talked about ZTransform and Fourier transform relationship. We talked about when ZTransform equals Fourier transform, what is the type of ZTransform function, what are zeros, poles, and what is Z-plane. And we talked about right-sided signal for which we find out the region of convergence. Today we will look into the left-sided sequence. We will find out its region of convergence, its pole zeros, and then we will move on to sum of two exponential sequences, and finally we will talk about the properties of region of convergence and stability and causality using the Z-transform. So let's get started. So here in this example is basically of left-sided signal, and this left-sided signal is exponential. You know that in order to find out the Z-transform or Fourier transform, we must have to sum the signal. So this is the signal x of n is equal to minus a raised to power n u of minus n minus 1. So this signal is basically starting from minus 1 and going towards minus infinity. Okay, so how we can take the Z-transform? This signal is non-zero only for n less than minus 1 as I've shown you here. So putting the value of x of n, there is a raised to power n u of minus n minus 1 z raised to power minus n, which is the formula of Z-transform, summing from minus infinity to infinity. Now you know that the limit for this signal is from minus infinity to minus 1. So we are replacing the limits from minus infinity to minus 1, and during this range this u of minus and minus 1 is 1. Okay, so we are only left with a raised to power n and z raised to power minus n. Now in order to simplify this thing, what we can do, we can shift the limits. Once we shift the limit, like if we add from minus 1 to minus infinity, it's just like adding from minus infinity to minus 1. So here we have flipped the limits from 1 to infinity, and similarly we have flipped this power of a and z. So ultimately if I put n is equal to 1, it becomes a minus 1, whereas in previous equation if I put n is equal to minus 1, it becomes a minus 1. So both of these are same. This is just for simplification, so we have just summation starting from 1 to infinity. Now in order to insert 0, we know that if I expand it from 0 to infinity, the first term will be a minus 1 z raised to power 0. So anything raised to power 0 become 1. So I have added n is equal to 0. So in order to compensate this, I must need to subtract. So 1 minus 1 becomes 0, and n is equal to 0 term will be cancelled out. Now in order for this summation to exist, this must be less than 1. As I've told you, this summation must be less than 1 so that we can apply geometric series on it. So if I solve this, a inverse z should be less than 1, or I can say z divided by a should be less than 1. It becomes z should be less than a. Okay. So z should be less than 1 is the region of convergence. So I can take any value of z which is less than a, our sequence will converge. So this one is this, and then for expanding this I can use geometric series. So first term divided by ratio 1 minus this ratio is the argument. So if I simplify this, it gets 1 divided by 1 minus a z inverse. So you must remember this form, because in example 3.1 the Z transform was 1 divided by 1 minus az, but its region of convergence was different. In previous case we were getting the region of convergence greater than A. But here the region of convergence is different, but Z transform are same. So in question, if I have the value of A to be 5, Z must be less than 5 so that this argument is less than 1. So here you can see that we are just randomly taking the value of A here in Z plane, and Z is equal to A is pole and Z is equal to 0 is our 0. So you can see 0 here, this is pole. Now this is region of convergence. So I can take all the value of Z that are less than A. Okay. So you must need to understand that whether the signal is left-sided or right-sided, the ROC is different, the Z transform will be same. Okay. So the Z transform of this x of n is this, and the inverse of this is x of n, provided the region of convergence is, when the region of convergence is Z mod less than A mod, x of n will be minus A raised power n, u of minus n minus 1. When region of convergence will be this, x of n will be A raised power n, u of n, and obviously, okay. The pole 0 plot and region of convergence for this example is shown in figure 3.4. As you can see, note that A mod is less than 1. You can see that A mod, the value of A is less than 1. This sequence grows exponentially as n approaches to infinity, and thus the Fourier transform does not exist. So in this sequence, when the value of n goes to minus infinity, it becomes exponentially growing. So in order to control this exponential growth, what we can do, we can take the values of Z such that A inverse multiplied by Z power n, this whole quantity becomes less than 1. Let's move on to the next slide. So here in this example, we have sum of two exponential sequences. One sequence is this, which is right-sided, and the other sequence is this, which is also right-sided. We know the Z transform of this will be 1 divided by 1 minus 1 by 2 Z inverse. So there is a pole at 1 by 2 and there is a 0 at 0. And for this one, the Z transform will be 1 divided by 1 plus 1 by 3 Z inverse. So there will be a pole at minus 1 by 3 and 0 at 0. Okay. Now the region of convergence for this, because this is right side, so region of convergence will be greater than this. So I can take all the values that are greater than 1 by 2. Similarly, the region of convergence of this will be all the values greater than 1 by 3, because region of convergence is always specified in Z mod. So Z mod greater than minus 1 by 3 ultimately becomes Z mod greater than 1 by 3. Now because there is a sum here, so after solving this plus 1 divided by 1 plus 1 by 3 Z inverse, if I take the LCM of these, this will become so 1 plus 1 by 3 Z inverse plus 1 minus 1 by 2 Z inverse. So 1 and 1, this will become 2, and then the LCM of 1 by 3, this will become 1 by 3 minus 1 by 2, the LCM will be 6, 2 minus 3, this will be minus 1 by 6. Okay, so 2 minus 1 by 6 Z inverse divided by 1 minus 1 by 2 Z inverse, 1 plus 1 by 3 Z inverse. So I solved this just to let you know the pole will be at 1 by 2, the other pole will be at minus 1 by 3. There will be two zeros. If you solve this quantity, if you solve this quantity and find out the roots, you will get one root will be at z is equal to 0 and the other root will be at z is equal to 1 by 12. 1 because there are two poles, there must need to be two zeros. So both are right sided. Z mod is greater than, so both are right sided. Z mod is greater than 1 by 2. Z mod is greater than 1 by 3. So overlapping starts after 1 by 2 because 1 by 2 is bigger. So the overall of region of convergence of these two signal will be Z mod greater than 1 by 2. Okay. So here you can see sum of two exponential sequence. Z transform of A this with ROC this. Z transform of B is this with ROC this. Z transform of C is this with ROC this. Okay. So let's move on to next slide. And this is the solution of previous example that we just did. This is x of, this is first term, this is second term. Then we took the Z transform and we opened the summation, there is geometric series of this one and this one, and we got this thing which I just told you. Then taking the LCM, it becomes this. So finding out the zeros and finding out the poles, you can have the pole zero plot that was shown to you in previous figure, and the region of convergence for which both signal overlap is Z mod greater than 1 by 2. Now example 3.5 is sum of two-sided sequences, exponential sequence. This sequence is right-sided because you can check this from this is function u of n, whereas this function is left-sided. Note that the sequence grows exponentially when n approaches to minus infinity because of this second term. So we know the Z transform of this first term is 1 divided by 1 plus 3 Z inverse, and region of convergence for right sided is always greater than 1 by 3, whereas the region of convergence of this minus 1 by 2 raised to power n u of n is 1 divided by 1 minus 2 Z inverse, with region of convergence less than 1 by 2. So once I solve this plus this, so we have plus here, and I take out the LCM. This is the same function as we had in previous example. So same function, but here one is growing beyond 1 by 3 and one is coming inside. So the overlapping of these two will take place between 1 by 3 and 1 by 2, because I'm just going to draw the poles here. So if this is 1 by 3 and this is, sorry, let's move on to next slide where I can show you more clearly. Let's move to next slide. So here you can see we have 0 at 0, 0 at 1 by 12, this pole is 1 by 2 and this pole is 1 by 3. So you know that the region of convergence was Z mod greater than 1 by 3, so we can take all the values in which Z is greater than 1 by 3, and the second was Z is less than 1 by 2. So if Z is less than 1 by 2, it means I can take all the values from 1 by 2 towards the origin, and it doesn't matter if I write 1 by 3 here, and I can take all the values that are greater than 1 by 3. So if you see here, the overlapping occurs when Z mod is greater than 1 by 3 and less than 1 by 2. So the region of convergence for this sequence will be this greenish region. So I can take all the values here. So this will be the region of convergence of this sequence. Okay. So From these examples, from example 3.1, 3.2, 3.3 and 3.4, we can see that infinitely long exponential sequence have Z-transform that can be expressed as rational function. We have seen that the Z-transform is always in the form of P by Q. It has zeros, it has poles, which we can express either in Z or Z inverse. The case where the sequence has finite length also has rather simple form. If the sequence is non-zero only in the interval, so we know that if the sequence is non-zero only in the finite interval, there is no issue in the existence of the Z-transform. The existence of Z-transform subject to region of convergence only when the exponential sequence is infinite duration. So whenever we have a signal with interval n1 to n1 to n2, it has no problem of convergence as long as each of the term is finite, as long as the magnitude of x of n is finite. For example, this x of n, if we take the Z transform of this, delta of n Z transform will be 1. How? If I substitute, this is the formula of the Z transform, n is equal to minus infinity to infinity, and this will be x of z. Okay, so x of z will be equal to summation delta of n z raised power minus 1. So we know that where this delta function is defined, this delta function is defined at 0 only. So it means I just need to expand it for n is equal to 0. So delta of 0 and z raised power 0. So z raised power 0 is 1, delta of 0 is 1, so its Z transform will be 1. Whereas for n plus n minus 5, the Z transform will be z raised power minus 1. Simply substituting delta of n minus 5. So delta of n minus 5, the sequence will be defined for n is equal to 5. So putting n is equal to 5, we will get z raised power minus 5. So because this is a right side sequence, and if I solve it, I can write it like 1 divided by z raised power 5. If I further solve it, I get z raised power 5 plus 1. So its poles are at z is equal to 0. So the region of convergence will be z more greater than 0. An example of a case where finite number of terms can be summed to produce a more compact representation of Z transform. So let's move on to example 3.6, which is of finite length sequence, and let's see how we can find out its zeros and poles. So example 3.6 is of finite length sequence. Sequence has the form a raised power n within the interval from 0 to n minus 1. So it has no problem as long as a is finite. We don't have any problem in summing this signal. So using the formula of Z transform, summing from 0 to n minus 1, the signal is a raised power n, and this is formula z raised power minus n. So taking n common, and we know that this is finite terms 0 to n minus 1. So the geometric series formula will be first term a z raised power minus 1 power 0, the first term, minus last term. So last term will be n minus 1 plus 1. So which will become a z raised power minus 1 raised power n. And then 1 minus this argument. And if we solve this, if we just simplify it, it becomes 1 divided by z raised power n minus 1, z raised power n minus a raised to n divided by z minus a. I can solve it for you. 1 minus a n z raised power minus n divided by 1 minus a z inverse. So if you solve this numerator, you can write z raised power n minus a raised power n divided by z raised power n divided by z minus a divided by z. So this z gets cancelled with this and we are left with z raised power n minus a raised power n divided by z minus a into z raised power n minus 1, because this z gets cancelled with z raised power n. So we are left with z raised power n minus 1. Now if you look at this, we have pole at z is equal to a, and then we have pole at z is equal to 0, and then we have zeros, n zeros at a raised power n. So how we can find these zeros? We can find these zeros with the help of formula. Now for a simple case, assume that n is equal to 2. So we'll have z2 minus a2 divided by z minus a 1 divided by z for a case when n is equal to 2. And this term gets cancelled with this, because z plus a into z minus a is z square minus a square divided by z minus a. So we get this term gets cancelled with this and we are left with this. So there is a pole at z is equal to 0 and then there is a 0 at z is equal to minus a. So for the case of n is equal to 2, we saw that these two roots are orthogonal. These two roots are out of phase. If one is at a, the other root will be at minus a. So whenever we have n zeros, all of these will appear with some phase shift. So for these two, they are 180 degree apart. So if n is 16, let's say, we can determine with the help of a e raised power j 2 pi k divided by n. Okay, so it means that 360 circle is divided into 16 portion. So it means that like this is 180 divided by 8, and then we have 90 divided by 4. So it means that 45 degree. Each zero is appearing after 45 degree, or you can use this formula. So for example, the zeroth, when k is equal to 0, the first zero will be on the real axis, because if you put k is equal to 0, e raised for 0 is 1. For k is equal to 1, or 0 will be a e raised for j 2 pi divided by 16. So the 0 will be at pi by 8. Pi by 8 is exactly 22.5. I guess I solved this wrong. Let me check it out. Okay, 4. 90 divided by 4. Okay, so this is 22.5, not 45. This is 22.5. So let's move on to next slide and see how the 0 appears. So these are the zeros that are appearing after pi by 8. So there was a 0 here, but there was a pole here, so those gets cancelled. Then this is 0, 0, 0, 0, all appearing after pi by 8 degrees. So there are 16 zeros here. You can find them all. 4 here, 4 here, 4 here, 4 here, and then this pole gets cancelled with 0. And these are 15th order pole, because one pole is here, 15 poles are here because of z raised power n minus 1. It is, if n is 16, so there are 15 poles at the origin. Number of poles and zeros are equal. Okay, so you just need to divide this circle into 16 parts and then you can get their 15 poles. So just by solving this expression, from here I can say there is a pole at A, there are 15 poles at origin, and then there are 16 zeros with phase shift of pi by 8. Let's move on to next slide. So these are the common Z-transform that you must need to understand and you must need to solve. For example, for delta of n, the Z-transform is 1. It means you can take all the values in ROC. For u of n, it means that it has 1 here. The Z-transform is 1 divided by 1 minus the inverse. And the region of convergence will be Z mod greater than A 1, because here we have 1. We don't have A here. And then this is left side sequence, so same Z transform as this, but region of convergence is opposite. For delta of n minus m, the Z transform is Z raised to power minus m. So we can take all the values of Z except 0. Okay, because I can write it like Z raised to power m. So if I take Z is equal to 0, it becomes infinity. So I can take all the values except Z is equal to 0. For A raised to power n, U of n, you know that what is the Z transform, and region of convergence for this one, we know the Z transform is this. Now you can find out the Z transform with the help of properties that we are going to discuss further. So if you know 1 to 6, you can easily find out 1 to 12, and then this 13 is the exactly same finite length sequence starting from 0 to n minus 1, and its Z transform is this, because all the poles lies at origin. So region of convergence is Z mod greater than 0. For the previous example, I can take all the values of Z that are greater than 0. Let's move on to next slide. These are the 8 properties of ROC, the region of convergence. So region of convergence is always a ring or disk in the Z plane, and it is always centered at the 0. Okay, so ROC will be a disk or ring. We can say that ROC, if there is a pole here, we can see ROC is either greater than this or it is less than 0. So it always make a ring or disk. Okay. Secondly, Fourier transform of x of n converges absolutely if and only if the ROC of Z transform includes unit circle. So for example, if there is a pole here at 0.5 and then ROC include this unit circle. If ROC includes unit circle, then Fourier transform exists. ROC cannot contain any poles. We cannot say that this is a unit circle, there is a pole here, and then there is a pole here at 2. We cannot say that ROC is greater than 1 by 2 because there is a pole at 2. So ROC never contains a pole. ROC can never contain a pole. If the sequence is finite, we have seen that the ROC will be entire Z plane. We can take all the values except 0 or infinity. There are only two possibilities that we cannot take, either 0 or infinity. Property 5. If x of n, if a sequence is right-sided, there is 0 for n less than 0. So in that case, the ROC will extend from outermost pole towards infinity. So if I say that I have like, this is the region of, I have pole at 0.5, I have pole at 1, and I have pole at 2. And this kind of a pole 0 appears from a right-sided signal. Then my ROC will extend from outer pole towards infinity. And Whereas property 6 says that if these poles point 5, 1 and 2 comes from a left side sequence, then ROC will extend from innermost two poles towards 0. Okay, most pole towards 0. Now, if x of n is two-sided, for example, one pole is here and other pole is here, and it is two-sided, then ROC will be a ring or disk. So this will be the ROC bounded region. Okay, between 0.5 and 2. Between 0.5 and 2. A two-sided sequence is an infinite duration sequence that is neither right side nor left side. If x of n is a two-sided sequence, the ROC will consist of a ring in the z-plane, bounded by interior and exterior of the poles. See, ROC must be a connected region. So this is a connection. ROC is a connected region. We are not saying like between 0.5 and 2, because between 0.5 and 2 there's an intersection. Connection means interconnection. It means that there is overlapping. So for example, z mod is greater than 0.5, it means from 0.5 it's going towards infinity. And if z mod is less than 2, it means it's going from 2 to origin. So their overlapping or their intersection occurs between 0.5 and 2. So these are the properties that you must need to understand in order to find out the region of convergence. Let's move on to next slide and see the stability and causality from ZTransform. So before we move to stability and causality, this is the pole zero plot of some random signal. So our goal is to find out the all possible region of convergences. So if I say that this pole zero plot appears from a right-sided signal, so the region of convergence will be z mod greater than c. So the region of convergence, as you can see here, I can take all the values that are greater than c. And when I say this plot in A is a result of left-sided signal, then the region of convergence will be this. Okay, between less than A. So this is for right side, this is for left side. So the intersection of all these, it means A is going outside, B is going outside, C is going outside, so intersection appears after C. Whereas here C is less than, Z is less than C, B is less than C, and A is less than, Z is less than A. So all of these are intersecting after A. Now in case of two-sided, if A is right side, B is right side, and C is left side, the overlapping appears between A and B. Likewise, if A is right side, B, here I can draw it for you. If A is left side, sorry, A is right side, B is left side, and C is left side. Whereas where the three lines cutting, they are cutting between B and C. Let me write it clearly. This is going here, this is going here, and this is going here. So the overlapping appears between B and C. So it means C mod is greater than A, Z mod is greater than B, but Z mod is less than C. So the overlapping appears between B and C. So this is two-sided, this is two-sided, this is left side, this is right side. Let's move on to next slide. So in order to find out the stability and causality from the ROC, so this signal is said to be causal if this unit circle is included in the ROC. If this unit circle is included in the ROC. So if we have a pole here and we have a pole here, what will be the ROC for signal to be stable? For your safe side, for your ease, I can draw 2 here. Okay, it doesn't matter because we are going to take the mod. So we can see that there is a circle, let's say here. If this is right side and this is left side, only then I can include this unit circle. So it means that Z mod should be greater than 1 by 2 and Z mod should be less than 2. So if this is the region of convergence, only then unit circle is included and the signal will be stable. For causality, the ROC must need to be right-sided. The ROC must need to be right-sided. If this is right-sided and this is right-sided, the overlapping appears after 2. So Z mod greater than 2. So if this is a circle of radius 2, 1 by 2 is greater than, and then the overlapping appears after 2. So Z mod greater than, the signal will be causal for this kind of RC, and for this kind of RC it will be stable. Okay, so it is very easy to find out the stability of the signal and causality of the signal based on the RC. Now this kind of a Z-transform, this kind of a pole zero plot or Z-transform cannot be causal and stable at the same time, because if we want to have a signal to be causal and stable at the same time, we must need all the poles to be inside unit circle. So if all the poles are inside unit circle and they are right-sided, only then I can have stable and causal system or signal. So that was about today's lecture. We will clarify rest of the things during lecture. Thank you very much.